Evening, everybody. It's 5 o'clock on Tuesday night. So time for some Calculus 2. Tonight, we're going to look at conics, talk a little bit about them, talk about, kind of brush over why they're so important. And then we'll look at doing a couple problems of identifying the pieces of conics. And then we'll definitely have some time for you guys to try a couple. Before we get to that, just a couple reminders. You've got access to the first take-home problem, so make sure you're taking a look at that, working on it. You can follow the instructions in there, but the biggest thing I don't want is for you to get stuck having to work on the take-home problems the night before they're due or something, because you want to be able to have some time to work on it, figure out what resources you want to use, how to solve the problem. So make sure you're taking a look at that and get started on the take-home problem. Also, we have our first quiz due, I believe, tomorrow over Module 1. If you've already taken it, great. But I wanted to remind you that there's a reviews for all the quizzes in course content. All you got to do is go into the module that you're taking the quiz for. You'll see the review right in front of the quiz. The quizzes are subsets of the reviews, so the reviews are a good way to help you prepare for the quiz. The quizzes are, just as a reminder again, this is stuff you'll be used to after you take the first one, so I won't do this every time we have a quiz. Quizzes have a 2-hour time limit. The timer starts from whenever you begin the quiz and is continuous for those 2 hours, even if you log out. All right, you can log out and you can log back in, but the timer will continue. So make sure you have a nice 2-hour window so you can get the full time should you need it. If you prepare for the quiz and get your notes ready and everything, you should be fine. So just make sure that just pay attention to the days for that. Like I said, I won't do this every time we have a quiz, but because this is our first one, just want to take the opportunity to remind you of that. Okay, let's talk about conics. So you've gone through the online lesson. There's a lot of information in there. We're going to bring up the online lesson a little bit today. One of the things, conics are really cool. We're going to talk about why they're so cool. One of the things that can be kind of scary, though, the first time you do conics is all the definitions, the focus, the directrix, the lattice rectum, all the stuff that goes with conics, the cofoci, major axis, minor axis for an ellipse. I don't want you to stress about that. You're not going to need to know have those definitions memorized for the proctored exam. Okay. Yeah, there'll be a quiz over conics, but the quiz will be open note, so you can have all that stuff ready. You won't have to worry about it for the exam. Okay, so I don't want you to be stressed about trying to remember all this stuff because there's a lot. What I want to take away from today is just a little bit of where conics come from, how they're created, and how we might see them in everyday life. And then again, we're going to look at a couple problems from a worksheet that I'll put into chat when we get to. Okay, so let's get into it. So I've got this applet up for conics because I think it does a good job kind of showing where these conics come from. Something interesting about conics from a historical aspect. The Greeks started studying conics because they started looking at the different ways to cut a cone. So for example, we've got a cone here, and the double cone would be more interesting for the hyperbola. And basically, if we were to cut a cone horizontally, so with an angle of 0, we get a circle. All right. No matter where we cut it, it's always a circle. Now, I don't think we need to spend a lot of time discussing the importance of the circle, right? The circle shows up all the time in everyday life, right? The tires on your car. We have circular surfaces everywhere, right? The glasses we drink out of, so on and so forth. So circles we're very familiar with and spend a lot of time with. It's these other ones that maybe we don't see as much. So when we start to cut the cone at an angle, we get the elongated circle or an ellipse. Okay. So there's our ellipse. And as you saw in the lesson, the ellipse, if we plot it on an XY plane, can be elongated in the X direction or the Y direction. And actually, it can be elongated in any direction because we can actually rotate the ellipse at any angle we want. We're not going to be doing that in this course. We're just looking along the X and Y axis. But ellipses show up quite often. We can think of a lot of things that have the shape of an ellipse. For instance, our eye has the shape of an ellipse. Like a football type would have the shape of an ellipse. But where ellipses really, so this is what's really interesting about conic sections, in my opinion. So the Greeks started cutting up the cone and finding these shapes, and then they found a lot of the mathematical relationships with these shapes that were talked about in the lesson. It wasn't until later that a lot of the real world uses for these shapes came into play. So one major use of an ellipse that was discovered well after the ellipse was discovered is that the planets tend to move in elliptical orbits around the sun. All right. So that was something that is, really interesting because if you look at historically, remember, there was a time when the thought was the sun revolved around the Earth. So it was a really major discovery to find that the planets revolved around the sun, including the Earth, and that their path wasn't circular, it was actually elliptical. Another thing that's elliptical are the electrons that go around an atom. They move in elliptical paths. Excuse me. There are buildings that are built that have an elliptical shape. And what's interesting about those buildings, let's see if I have a picture of one. Yeah. So I got a few pictures, not a bunch, but these. So they call them, whispering galleries. The Morven Tabernacle is also one. And what's interesting about these is the roofs are built in the shape of ellipses. And what happens is if you stand at one foci and maybe drop a pin or whisper, somebody standing at the other foci will hear it at the same level that you do because all the sound reverberates off that elliptical ceiling and goes down to the other foci. So they've got a lot of really cool properties. I don't have it on this one, but there is also actually got it here. This one is kind of cool. The elliptical pool table. So with the elliptical pool table, if you hit the ball through one focus, it will bounce off the sides and go in the other focus. So again, it follows just the properties of the ellipse. So somebody had actually built and manufactured and sold these elliptical pool tables, but nobody could figure out the trick to making it. So they never really caught on to making the ball in the hole. So ellipses, again, they found this shape of the ellipse by cutting the cone at an angle. And they started finding all these mathematical properties about it. Just started studying the ellipse. It wasn't until a few hundred years later when they were really where astronomers were really starting to dig into studying planetary motion, that they found started finding uses for the ellipse. Ellipses are also used for stage lights in theaters because it helps the light reverberates off of all of these. Say there's mirrors on the ellipse and maximizes the beam. Okay. again, this is just kind of a general, hey, why do we care about conics? Some cool stuff about conics. We'll get into solving some stuff about conics here in a little bit. Now watch what happens as we change the angle. Let's move this up a little. So we change the angle of the plane, the ellipse gets longer and longer until eventually we don't have an ellipse anymore. Okay, there we've got our hyperbola. The hyperbola is when the plane cuts at such an angle so that we get the two pieces. We get a cut on the top cone and the bottom cone. Hyperbolas are really interesting and have a lot of cool properties too. There's a lot of overlap between the properties of hyperbolas and parabolas because they're so similar. So a lot of things we'll talk about with parabolas also work on hyperbolas. But a couple that are unique to hyperbolas would be sundials. You know, sundials for telling time worked in a hyperbolic fashion. Paths of particles. Lamps actually create a hyperbola. Right here, if you have a shade on the lamp, creates a hyperbola above and below. Cooling towers of nuclear reactors are hyperbolas. So they show up quite often. Now, if we keep increasing this angle, eventually we won't cut both sides. And so let's move this up a little. Oops, do the angle the other way there. And we are going to get our parabola in between that hyperbola. Can't quite get it on this one. Right in there, when we're crossing over from the ellipse to the hyperbola, we're getting a parabola. So let me show you a picture of it. Since I can't get the app to do it at the moment. Because again, this is where these came from. All our conic sections came from just, hey, we got a cone, look at all these cool things we can cut it into. So there you can see the parabola. Should be like about right there. For some reason, can't quite get it. Should be that one right there. But the parabola also comes from cutting a cone at an angle. All right, a little bit steeper angle than the ellipse, not quite as steep an angle as the hyperbola. Parabolas are again, being able to make something in a parabolic shape has a lot of amazing properties in that anytime we bounce off the sides, it's directed through the focus. So one major application of a parabola is, of course it's on the other one, a satellite, okay, or auditory devices. Because what happens is all those rays, all those waves come in and they're going to bounce off this satellite, but there's our focus right there. So you got bombarded with terms in the online lesson: focus, directrix, lattice rectum. They all have real world applications. Also, for instance, headlights on a car, or light beams coming out of a light tower. Those also are parabolic because what they do is they put mirrors along here, and what that does is that amplifies the beam through the focus. So these shapes that were kind of arbitrarily found by just taking a cone and cutting it ended up being amazingly important to the technology that would come hundreds and hundreds of years later. So I think that's one of the interesting things to me about conics is that they were just discovered trying to, by just playing around with the cone and seeing that there were all these cool mathematical properties. It wasn't until later that the uses for them actually came about. Yeah, John Paul, I saw your message. It's there. You can't see it. You know, like in between the ellipse and the hyperbola is our parabola. It just doesn't say it here, and I just think that's something on the app. So that's just my quick little brief introduction into why conics are cool. They're very important. Now let's talk about what we're going to be doing with them in here. So I'm going to throw this worksheet in chat because this is going to be the worksheet we're working with today. What we're going to do today is take some time to identify the type of conic section we have, and then identify some of its important pieces. Its vertex, its vertices, its foci, focus, if it's one or two, that sort of thing. And I'll talk about some of these pieces as we go along. All right. Because they all have, you know, we've noticed there's a lot of overlap. So what we're going to do is we're going to do a couple of them together from this section. And I'm going to have you try some from 17 through 22. Because there's a couple reasons I want you to do it. Number one is obviously for a little bit of practice on how to use the formulas. Number two, one of the things that's going to be needed is to write these conics in standard form. Now, when you get to the homework, you're not always going to have to do that. Some of them will already be in standard form, but some of them won't. To write them in standard form, you have to do completing the square. So I wanted to do a couple where we have to do completing the square because probably haven't done completing the square in a little while. And it's going to be nice to have a little refresher. So let's start off with number 10. So we have negative 2y squared plus x minus 20y minus 49 equals 0. Now, if without even going any further, we should be able to identify what type of conic we have. So the first thing you look for is how many squared terms do you have? We have a y squared, but no x squared. If that happens, then we already know which conic we have. It's going to be a parabola, because a parabola is the only one that has only either x squared or y squared, but not both. If both are squared, we still might have a circle, we still might have an ellipse, or we still might have a hyperbola, okay? So right off the bat on this one, you can already say, okay, well, we definitely have a parabola. Now, the next thing we're going to want to identify on a parabola is whether it opens to the right, left, up, or down. Well, because the y is squared, we know at this point it's going to open right or left, not up or down. Now, that's not something I'm expecting you to memorize. That's actually kind of easy for us because we're used to parabolas that look like y equals x squared, and we know that opens up. So if the x is squared, we know it opens up or down. If the y is squared, we know it opens right or left. And again, we're just using some pre-existing knowledge for that. Again, guys, like I said before, I know some people have joined since I said it earlier. A lot of terms in this section. You do not have to memorize any of them for the proctored exam. So feel free to use notes as you go through homework. I don't want you focused on memorizing what the lattice rectum is or how to find it. I just want you to be able to take the formula and identify it. All right. So we've got a parabola in number 10. So here's what we'll do. Once we know, sorry, I'm going to have to go back in there real quick. All right, so once we know, I'm going to do it off the lesson, but guys, if you have this written down in notes, or if you have like a short-handed sheet that you like using, that's totally fine. All right, so we got parabolas, and the definition of a parabola is basically a curve whose set of points is equidistant from the focus and the directrix. So let's see. This is just, we'll give you, here's the directrix, here's the focus. You guys didn't get a chance to see this. It's a pretty cool animation. I'll let you guys play with that. But we'll come down here. So this would be our, so we got our parabola here. Let's move, you guys can see it. And the directrix is this line here. We can move the directrix. So let's move it to directrix to -5. Notice that the 2 points, the points on the curve, are always the same distance from both the focus and the directrix. That's the definition of a parabola. All right. Now we said we're going to have a parabola opening left and right. So here's the general form. So now what your goal is to rewrite the parabola in this general form. Okay. So, because once we have it in this general form, everything is right here for us. So we're going to leave the y terms on one side. So minus 2y squared minus 20y. And then I'm going to move everything else over to the other side. So I'm going to do completing the square on this. Equals -x plus 49. Now, let's not deal, since both the y squared and the x are negative, what we'll do is we're going to make all of that positive by multiplying both sides by a negative. So we're going to have 2y squared plus 20y equals x minus 49. Okay, we're going to be doing completing the square, which means we're going to have to add something over here. To compensate for that, we'll add something over here. Don't worry about what it is yet. I'm going to show you a way of coming up with that number very easily. Now, when doing completing the square, you always want to have a 1 for your coefficient on y squared. So I divide by the 2, and I get times y squared plus 10, and then I'm going to have that plus something there. Over here, x minus 49 plus that something. All right, go down to the next line. I've got 2. This will be y plus. What we're going to do is turn this into a perfect square so it factors into 2 identical factors. So this number right here is always half of this number. If this number is positive, it's plus. If this number is negative, it's negative. So we take half of the plus 10, which is plus 5. That is our perfect square. Now, what we're going to do is we got to fill in what the number is here. Well, if we were to FOIL this out, we would get y plus 5 times y plus 5, which would put 25 right there. That is a perfect square. That factors into y plus 5 times y plus 5, hence completing the square. But I changed what I originally had. So the number that goes here, remember, anything in these parentheses is getting doubled. So let's write it this way so that it's really obvious. 2 times 25. Well, if I add 2 times 25 to that side, I've got to add 2 times 25 to this side to keep everything balanced, or 50. All right. Last thing we got to do, finish this guy up. X minus 49 plus 50, so x plus 1. And lastly, notice that we've got this coefficient over on this side. All right. We want to make sure we match that. So that means that 2 over here, I want to take it to the other side. So I'm going to multiply both sides by 1/2. Okay. Now we've got the standard form of a hyperbola. That comes from completing the square. Questions so far?
For the fourth line, when you were starting to factor it out, is the 10 supposed to have a y next to it?
It sure is. Thank you.
Okay, no problem.
I totally forgot it. Good catch. Yeah, because what we did, all we did from here to here is factor out the 2 out of these first 2 terms. So it should have been y squared plus 10y. Thanks, John. Other questions about getting to here? All right, now we identify the pieces. So for instance, the vertex, h comma k. So h comes from, h is always teamed up with the x term. That goes for all of these. And notice the sign is opposite. So -1. And same thing with the k. The sign is opposite and it's teamed up with the y term, -5. All right. Now, in order to find the focus, we need this p. Where does it come from? Well, 4p is equal to this number that sits out here. All right. So what we do is we say, okay, 4p equals 1/2. Divide both sides by 4. And what does that give us? That p equals 1/8. All right. So this will allow us to find focus. Now, here's one thing I want to point out. We already said we had one that was opening right or left. Well, because there's no negative on either side, usually we'll put it on this side with the 4p. Because there's no negative, this thing is going to open right. So we can say parabola that opens right. All right, so if we were drawing a rough sketch, we've got a vertex -1, -5. Parabola is coming through like this. That means the focus is going to sit over here. Now, how do we get the focus? We add p to the x value. That's what I'm showing you. You don't have to have a perfect sketch, but a rough sketch. So we want to make sure we move to the right 1/8, not to the left, up, or down, because the focus is going to be to the right. So -1 plus 1/8 is -7/8, -5. So that's that focus there. The directrix is the exact opposite direction. The directrix is that vertical line. And notice for the directrix, you subtract p. And it's a vertical line, so it gets the equation x equals. Now we're going to subtract 1/8 from -1. So -9/8. The eccentricity, because we'll be finding the eccentricity for all of them, and I'll talk about it here in just a second. The eccentricity for parabolas is always 1. All right, that's a characteristic of a parabola, and that's because of that property that the focus and the directrix are always equidistant from any point. So we get an eccentricity of 1 for all parabolas. The eccentricity can be thought of as a measure of how circular something is. So what's interesting, for a circle, the eccentricity is 0 because it is a circle. For a parabola, the eccentricity is 1. So where it gets interesting is on ellipses and hyperbolas. And so when we're going to do a hyperbola next. So we'll explore how the eccentricity changes as we change a hyperbola. But the eccentricity gives us information about how curved a hyperbola or an ellipse is. So an eccentricity doesn't give us information about a parabola or a circle. Last thing we're going to find on this is the lattice rectum. The lattice rectum now is a line that goes through a focus and whose both ends lie on the conic. It's a chord. For a circle, the lattice rectum is the diameter. We'll look at one for the hyperbola. For an ellipse, it would go through either focus because it's going to be the same, and then it hits both sides. It doesn't go through both foci. It just goes through one or the other. It hits the two sides of the ellipse. So to find the lattice rectum, that is the 4p value. We already had identified that as 1/2. And there is all those pieces about our parabola. So like I said, guys, you do not need to memorize any of this. You just need to know how to use it. So if you have a sheet that has this on it, that's all you're going to need for going through the homework and for taking the quiz. Okay? I'm not going to ask you this kind of stuff on the proctored exam. We'll talk more about what will be on the proctored exam later. What I just don't want you to be stressed about. This is a lot of information in this section. It's not stuff I'm expecting you to memorize. Okay. So this is going to be what you're going to be doing in your groups here. We're going to do one more just for a little more practice. But before we go to the next one, any questions about this one? All right, let's do a hyperbola. Ellipses are pretty similar. Because there's one thing I want to show you that's a little different than for ellipses and hyperbolas that's different than doing parabolas. So 15, we'll take a look at. This is from the worksheet. So 15, we got negative 9x squared plus y squared minus 72x minus 153 equals 0. So right off the bat, I know it's a hyperbola because there's an x squared and a y squared, so it can't be a parabola. And the x squared and the y squared have different signs. All right. If they had the same sign, it's either an ellipse or circle. And the only way it's a circle is if the x squared and the y squared have the same coefficient. If they have different coefficients, it's an ellipse. So you can tell without having to do completing the square what you have. All right. 12 would be 12 here would be a circle. 14 would be a parabola. 13 would be a hyperbola. So you'll know once it's right away. And so then what you're going to do is you're going to pull up the formula. There's two options for hyperbolas, opening left and right or opening up and down. All right. So how do we decide which one's which? Well, we go by which term is negative. So if it has a horizontal axis, that means opens left and right. It's if the y squared is negative. Vertical axis is if the x squared is negative, which is what it appears we have because we've got a negative x squared there, but we'll see because we're going to have some division. So let's start off assuming that we're looking at a vertical axis. All right. And what we'll do is we'll work it out algebraically, and then we're going to take a look at that and talk about eccentricity. All right. So what you do, because now we're going to have to complete the square possibly in the x and the y. You're going to group all your x terms and all your y terms, complete the square on them separately, and then divide so whatever you have is equal to 1. Since we have that one negative, I'm going to group our y terms in front. I only have the one y term, so I won't have to. So I won't have to complete the square in y. But if there was like a 25y term, I put plus 25y, leave a space because I got to complete the square in y. Okay. Now minus 9x squared minus 72x, and then I'm going to be adding some number on the end. I'm going to take the 153, bring it over to the other side with addition, so equals 153. All right. So we only have to complete square on the x, but if there was another y term, we would do it for the x and the y. So y squared, factor out any coefficient on the squared term. So I'm going to pull up the -9. So I've got x squared plus 8x plus something equals 153. Again, we're going to have to, whatever we're doing on this side, I've got to do on this side. Okay. Now this next step should look just like what we did last time. The y squared -9. X, what number goes here? Well, we have +8 here. Divide that coefficient by 2. So +4 squared. What number goes here? 4 squared. For notes purposes, I'll put 4 squared there. Okay, now we backfill. So what goes here? Well, 4 squared is 16, but to pull it out of this set of parentheses, it does have to be multiplied by -9. So -9 times 16. So -9 times 16. So that's a -144. Sorry about that. All right. And that 153 minus 144 is 9. Before I go to the next step, any questions so far? This is what, like I said, the ones you're going to do, you will have to complete the square. So you're going to get practice on this today. And I just want you to feel comfortable with completing the square. We're not going to do it a lot this semester, but it does show up on occasion. Okay, now the next step is the same, whether it's a hyperbola or an ellipse. The only difference is if it were an ellipse, this would be plus instead of minus. This has to be a 1. So we divide everything by 9. Actually works out kind of nice on this one. So we end up with y squared over 9 minus x plus 4 squared. I'll put over 1, but you don't have to, equals 1. There is the formula for our ellipse. It is now, or excuse me, hyperbola. It is now in this form. Okay. We can now find everything that's on this list. I don't have it on the list, but there is a center to a hyperbola. It's the same as finding a vertex. So the center, well, what makes that 0? -4. What makes that 0 is 0. So there's our center. The center is nice because it makes it easier for me to think about finding the foci and the vertices. Notice for the foci, we're going to be doing k plus c. Well, we need the c value. Well, to get c, we need a and b. A squared is this guy here. The a squared is the 9. The b squared is the 1. So a equals 3, b equals 1. Therefore, c equals square root of a squared plus b squared, or square root of 10. So now I can find the foci. What we're doing is, again, this is one that opens up and down. And bring this just over just a little so you can kind of see. We'll match it up here with the one on here in just a sec. But so what have we found? We found the center. The foci are going to lie above and below the vertices. So we're adding and subtracting root 10. So there's -4 positive root 10 and -4 negative root 10. All right. So actually, let me do this. If I bring this down a little, we'll be able to get it all on here. There we go. All right, so I can add the foci. We just found those two foci. Well, let's get this matching up. We have y squared over 9. So h is -4. So he's shifting over there. Our k is 0. Our a, which if we go scroll back up, a is under the term that comes first, or the positive term. B is under the negative one. So our a is 1. Our b is 3. All right. And there are foci. 3.16 is roughly the square root of 10. So our foci match up very nicely. Our vertices. The vertices are kind of like the vertices on a parabola. It's this point here and this point here. To find the vertices, you can kind of see it. I know it's kind of small now, but to find the vertices is very similar to finding the foci, except all you do is add a and subtract a from the k value. A is 3. So -4, 3, and -4, -3. Those are our vertices right there. We can find the asymptotes. To find the asymptotes right here, y equals k. Now k is 0 for ours because it is sitting on the x-axis. So it's going to be, we're going to have 2 of them. We're going to have plus and minus a over b. So 3 over 1 times x minus h. Well, our h was a -4, so x plus 4. We can add the asymptotes. That's what the asymptotes do. They give the behavior of our hyperbola. Not the short run, but the long run. So these are what we would call slant asymptotes because they're not horizontal or vertical. And those asymptotes really show the long run behavior of the hyperbola. That's where they tend towards. What else do we want to find? Let's find the eccentricity. Let's find the lattice rectum first, and then we'll do the eccentricity. Because I almost time on that. The lattice rectum, and I actually don't have it on the list because I'm not going to make you find too many of the lattice rectum, but the lattice rectum for a hyperbola that has a vertical axis is, again, not a formula you have to memorize. 2b squared over a. B is 1, a is 3. So 2 times 1 squared over 3. Oh, shoot, I got that backwards. Sorry. All right. And I'll show you the lattice rectum here in a second so you can see how it matches up with the hyperbola. 2a squared over b. Because we can see how wide it is. Remember, it's going to be a line that goes through the focus. So if we show our lattice rectum, there, it's going to be a longer line. So we actually want, in this case, the 3 up there. So 2 times 3 squared over 1, or 18. So the length of that lattice rectum is going to be 18. And you can see it's real similar to the lattice rectum on a hyperbola, on a parabola, excuse me. All right, last thing, eccentricity. Very simple, c over a, we already have those values. Root 10 over 3. All right, now, it should show where it's calculated. What I want to show you is what happens as we change the eccentricity. So let's take off some of this other stuff. It should be on there, and I don't see it. Huh, now it's not showing the value of our eccentricity. Okay, so that's okay. But notice, here's what I want you to notice. With A being 3, we get rad 10 over 3. Now watch what happens as I increase. I have these backwards, don't I? There we go. There we go. That looks better. Watch what happens as I increase A to our hyperbola. See how it gets less curved? It gets more curved. What that's going to do is that's going to increase the eccentricity. And if we come this way, it becomes less curved. So when we're talking about eccentricity, and there you can see it with A, we're talking about how curved these things are. Let's get back to what we had. There we go. And there is our hyperbola. Questions at this point? So by all means, guys, feel free to have lesson 2 open if you want to use that and use some of the apps that are in it. Or if you have a sheet that you like using, that's fine as well. Basically, what you're going to do is find some of these things. You're going to take a general quadratic, put it in standard form so that you can identify things like the center, foci, and vertices. It's basically going to be similar to what I just did. And I want you to use the formulas when you do it, okay? Just in case it didn't get, anybody didn't have it, here's the worksheet. And we'll do 3 groups today. And so these will be the problems you're going to do from the worksheet. I'll put these once you split as well. All right. So you're going to try 2 of them. This is just to give you some practice with completing the square. Everybody's getting 1 parabola and 1 not parabola, just so you can kind of see the difference between the 2. All right. Again, your job is to put it in standard form and then use the formula to identify what you're asked to find on the worksheet, which for the parabola, you're going to find the vertex and the focus. If you get a circle, you're going to find the center and the radius. And for ellipses and hyperbolas, you're going to find the center, the vertices, and the foci. And if you get an ellipse or hyperbola, go ahead and find eccentricity too. You're going to get asked about it in the homework, so might as well practice it. You're going to have all the information for it. All right. Any questions about what you're going to do once you're in groups? Okay. All right, you should have invitations to rooms now. You know, if you have questions as you're going through this stuff, by all means, call me in and we'll take a look at it. Probably, you know, we'll probably work on this for about the next 30 minutes, and then we'll just come together at the end just to recap anything. So go ahead and in your groups, you'll get started on these. Okay, guys, welcome back. Good job. You know, once you have your solutions ready, don't forget to post them to the forum. Just make sure you have a complete solution. Send out the answer key so you can check out your answers. All right, I wanted to show you something to kind of give you a little bit better feel for eccentricity. So eccentricity of 0 is a circle. Now you can't really see the circle because it's really small, but if I make it bigger, you can see the circle here. And an eccentricity between 0 and 1 is an ellipse. See the foci moving apart? So an ellipse where the foci are at the same point is a circle. So we start moving the foci apart. We start to get our ellipse. These are directrices. Each one of these is a directrix for the ellipse. Now let's go back to the non-fixed width. You can see it a little better what happens. All right, so watch what happens as the eccentricity gets higher. It gets more elongated, which is what I was trying to show with the hyperbola, but I think you'll see it better here. So we keep getting longer and longer. And eventually, still an ellipse. Once we get to 1, let's see, I don't know if I can get to 1 exactly or not. right here, this, even though we can't see it, oh, geez, I might have to recenter. Oh boy, that got a little out of control. Let's see if I can get this back. All right, let's recenter this. Okay. Once we get to 1, we know we have a parabola. Once we get over 1, we have a hyperbola. Now watch what happens as the eccentricity gets larger with the hyperbola. It gets more elongated in the vertical direction. So that's what the eccentricity is telling us. Closer to 1, it's a little more curved in the hyperbola. For the ellipse, it's always curved. It's an ellipse, but it's much more elongated. This curve is much sharper than if we go down lower. So this app, I think, is nice for giving a little bit of a feel for the eccentricity. Now, this is something you can play with the apps that are in the lesson. So for instance, here's the one for ellipse that we didn't do yet. The reason we didn't see the eccentricity on the hyperbola is because I had moved the applet around. When you move the applet, sometimes things don't end up where they're supposed to be. It was still there, it just wasn't, we weren't able to see it. So if you turn on the eccentricity, well, first off, we can create a circle by letting both foci be the same. The eccentricity is 0. Now, like we were seeing in that app, the longer it gets, the higher the eccentricity gets. What happens if we start to round it out again? Eccentricity goes back down. You lose those sharp edges. So the eccentricity basically tells us how sharp those turns are on our ellipse or on our hyperbola. And guys, you can play around with this, have it show things, lattice rectum, the vertices, to kind of get a feel for how these things relate to the graphs. All right. Again, can't stress it enough. You do not need to memorize these terms. The stuff you will do with Conics, you will have access to your notes, the lesson, these apps. So what I want you to do for the, as you go through the homework, use your notes. As you go through the quiz, use your notes, and don't try to memorize the stuff. Just be familiar with how to use it. All right. Okay, that's what I wanted to cover today. Any questions? And as always, if you don't have questions now, that's okay. Remember, you have access to the tutoring through SEC, through BrainFuse. There's the forum. You can always email me questions. So always remember that you have access to help outside of class. Conics are a very cool topic. We're really just scratching the surface of all the cool stuff they can do. You know, we looked at a few of the real world examples. You know, it's a fun rabbit hole to go down. You know, if you want to look up some videos on YouTube about conics, you can start to see how prevalent they've been in history and how used they are today, and a lot of things we use every day without even thinking about it. So if you don't have any questions, we'll go ahead and end there. And for Thursday, we have polar, either polar or parametric. I can never remember which one we do first, which will be a cool topic. You know, make sure you go through the online lesson before class on Thursday, and we'll pick up from there. We'll do kind of like we did today. We'll go through some examples, and then time permitting, work on some problems in groups. All right, if you don't have any questions, then I'll put up the recording from today. I'll have that up tonight.